Okay. So yeah, the terminology, the term is generative adversarial networks. Okay, so there are basically two key terms. First one is a generative model. And speaking of generative, actually we had a little experience in the last lecture about within this Gaussian mixture of Gaussian models. So the process of selecting data points from multiple Gaussian distributions, it's a kind of a generative process, right? We need to select the distribution, and within each distribution selected, we will draw a number from that distribution. Okay, so that's a way to generate a data point out of some abstract distribution, right? So that is a one kind of generative model. Okay, so the generative adversarial networks GAN as a generative model here, it's also generating data, and also that data points should comes from some distributions. Okay, but in this case we don't actually care too much about the what kind of distribution that the data point is from, but we the priority goal here is to make sure that the generative model can generate data points that are very close to the real data points. Okay, so the generative data should be as close to the real one, to the authentic one, as close as possible. Okay, so that is the one of the basic goals of GANs model. Okay, so we'll look at what it is, and particularly from some examples to see what it can achieve. Okay, and actually there will not be too much information about implementation. Okay, but we will go through some of the technical parts in the very first generation, in the very first version of GANs model, which is proposed in 2014 here. All right. So a little bit comparison of this generative, this term generative. Okay, so the term generative is, you can think of it as opposed to the other word, discriminative models. So far, all the models that we have talked about in this course is basically discriminative models. And their goal is to classify, for example, use the features, use the given features X to predict a label Y. Okay, so use the mathematical language. It is to model the probability of Y given X. So the Y should be at the left of this bar here. The probability of X should be here. So X is known because X is the feature. So the X is towards the right. So X is the condition. So we are modeling the conditional probability of Y given X. Okay, so that is the discriminative way of looking at the models. Okay, and right. So, for example, in logistic regression, we interpret the output from this sigmoid function as the probability of that data points belongs to the class Y equals 1, given that data, right? So it's a discriminative model. But on the other hand, the generative model is it's basically the opposite. It is given a label Y, and it tries to predict the feature X. Okay, so it's modeled the likelihood of the data given its label, and the probability Y. Okay, so for example, we had a little bit experience in the last time. We have a bucket of 2 fish, right? We have tuna or salmon, right? So we basically want to measure the likelihood of the data points given a class which is like a tuna, right? And of that data points times the probability of tuna fish. Okay, and this probability is the so-called prior. Okay, so it measures basically how likely in general a fish is to be tuna as versus to salmon. Okay, so it's the opposite of the discriminative models. And but so far in our course we didn't have much experience with it, and in the GANs model that we talk about today will have some, you can basically find some ideas of applying these generative approaches by generating features given the label. So let's look at some concrete examples of the current models. Well, actually, before that, actually, the GANs is not the only type of generative models. And this, from the Wikipedia page, we actually can find that it's actually quite a long run of studies already. Before GANs become very popular nowadays, we actually have variational autoencoders. We have Boltzmann machine and flow-based generative models, and so on. A lot of different ways to basically conduct the similar task as what GANs can do nowadays. Okay. All right. So let's see a little bit history of GANs. It was first proposed in 2014. Okay. So the very first version of GANs at that model in that year can generate like human face images in black and white or handwritten digits, and animals pictures. And those pictures, so these pictures are not real data, not real world images, but they are generated by the the generator component in that model, which is from a random distribution, which is from a random vector z from some distribution, right? And all the pixels are generated from these selected random vectors. Okay. So as the models being developed and further improved, you can see that the human faces generated by the GANs is becoming more and more real, and more, there are more details contained, and it's really hard to like distinguish it from actually a real sample, real human face. Okay. So maybe in 2015 and 16, the faces are still, recognizable, because some of the detail, if you zoom in bits, so all the pixels, for example, in the eyes, in the hairs, are just not that, real, not that real faces. Okay, so you have a question, Matthew?
Yeah, I do. So were these models just training for a longer period of time, or are they new models that are improving from 2015 to 2016, that type of thing?
Are new models. So they're basically new models. So for example, the GAN here, the first generation GAN, there's no convolutional structure in it. But the first GAN proposed using deep convolutional networks is the DC GAN here. Okay, you can see it's a much more color information and more details as compared to the non-convolutional evolution, from the non-convolutional predecessor here. And also, it's not just about the model structure, but also about the training techniques. Actually, it's more about the different tricks to generate the images. For example, the progressive growing GANs that set up multiple layers to progressively generate images, rather than generating the image all at once. So it actually is very successful in creating more realistic human images. So these are from the pictures in 2017. And I guess the nowadays the state of art is the style GAN and the style GAN version 2. I think it comes out last year. And all these pictures, oops, are very high resolution. And if you go to their websites, actually you will see a lot of difference. And even in the paper, they included, they published, there's a lot of high resolution images. So all these images are not real world human faces, but all generated models, generated by the models. Okay, and of course, to train again is very expensive. You need to work on pretty large data sets, and that is not the most expensive part, but it's really the hardwares. It's really the GPUs that you need to have, because you need to take inputs a lot of images, and the way that you set up the model contains tons of parameters that downsample the image and on the upsample the image again. Okay, so it's a lot of memory consumption needed, which are basically provided supported by GPUs. Okay, and I guess this style GAN 2 work is from the NVIDIA, and they have a lot of GPUs. They have a lot of researchers enthusiastic in using GPUs to do incredible jobs. Okay, so that is the kind of the state of art in style GAN. And GANs can be used to do a lot of things other than generating human faces. Like you can do artistic style translation. Like you can, given a real world photo, you can basically transform it into an art, right? You can like paint the horse with zebras stripes, and you can change the style of the pictures, right? The styles of the photographs, and so on. Okay, so that's the style GAN in 2017. Right, so I have this video that actually kind of it has a 1 million click now, and it's a 2019 paper that they use a GAN structure to model to achieve the few shot adversarial learning of realistic neural talking heads. Okay, so there are actually several different applications that all fall into this category of talking heads, and I think this is the best example here. Let's look at the video a little bit.
We present a system that can
you hear the sound?
Yeah.
We can, yes.
realistic talking head models. Notably, learning of a new head model requires just a handful of images. In this example, the model was learned from 8 frames. Once a talking head model was learned, it can be driven by the positions of the face landmarks. In this case, we extract landmarks by running an off-the-shelf face landmark tracker on a different video of the same person. Effectively, the learned model serves as a realistic avatar of the person. Our talking head models work well, even for new view angles, not present in the training examples, as shown here. Our system can learn from different numbers of frames. One-shot learning from a single frame is possible. Of course, increasing the number of frames leads to head models of higher realism and to better identity preservation. Our approach uses a meta-learning stage, which is performed on a huge dataset of videos. For the results in this presentation, the VoxCeleb2 dataset is used. 3 networks are trained during the meta-learning stage. The embedder network maps frames concatenated with the landmarks into vectors containing pose-independent information. These vectors are used to initialize the parameters of adapted layers inside the generator network, which maps landmarks into the synthesized video. Finally, the discriminator network assesses the realism, pose, and identity preservation of the generated frames. Better identity preservation is achieved via having a trainable embedding vector inside the discriminator for each training video. For more details, please refer to the paper. After meta-learning, we're able to fine-tune the generator and the discriminator for a new person. The generator and the discriminator networks have tens of millions of parameters. Still, such fine-tuning is possible on just a few images thanks to the good initialization provided by the meta-learning stage. Before fine-tuning for a new person, we initialize the adapted parameters of the generator and the video embedding inside the discriminator using the output of the embedded network.
Yeah, that's a little bit too more technical information. So let's see the effects.
Applying the system to famous photographs. In each case, we automatically find people in the Vox Celeb 2 dataset with landmarks suitable for the animation of a particular portrait. With a certain degree of success, we can even apply the model to paintings, despite the large domain gap between paintings and YouTube videos. Here, we can see that in some cases, the model might be very sensitive to the geometry of the landmarks. Driving Mona Lisa with landmarks from 3 different people results in videos with very distinct personalities. Landmark adaptation and tighter integration of our system with landmark tracking remains future work.
All right. So yeah, it's pretty amazing technique. And actually, I think there are already services that you can use. I don't know what website it is, but it's like you can upload pictures, static pictures, could be the old picture, and then it will generate a clip of animations, that picture talking, or just moving his head around, looking at different angles. It's like creating a like a portrait, a magic portrait in the Harry Potter movies that from a static image. Yeah, and that's something you can look into. I guess it's also that kind of service, that kind of product is also backended by this GANs model. Okay. Oops. All right. And this website is also something you can check out. It's called "This Person Does Not Exist." So there will be randomly generated images, human faces, but that are not actually real persons, but it's just a randomly generated generated by a model a GANs model trained from a very big data sets. Okay. Yeah, it's just something you can check out and to have some sense of what the current GANs model can achieve. Okay. So let's enter this technical part about the very first version of the GANs model. Okay. All right. So the idea is to set up two set of components, which is a generator and a discriminator. And these are all just the models. Okay, for example, the generator model, you can think of it as a reversed convolutional network. Okay, so it's like, so a typical convolutional model will like compress the data. Like you have a 10 by 10 image input will result in a 8 by 8 output volume, for example, right? For each convolutional layer. But in this case, the direction is the opposite. The smaller input will get basically upsampled into a larger intermediate variable. intermediate representation. So the generator will take some random inputs here. It can be a random short random vector, and its outputs will be some fake data. It's something that's at the same dimension of an image, but it's just a randomly generated fake data at the beginning. Okay, so that fake data or fake image will be compared with some real data. Okay, so that data is the target data sets that you wish the generator to learn from. Okay, so it could be a set of human face images, or it can be a landscape images, or whatever images you want to generate. So that'll be the real data, and that data will be compared with the fake data and feed into a second data set, second model, which is the discriminator. I think I didn't put the label here. So this set is the discriminator. So it's a typical convolutional layer, convolutional network. So which shrinks the data volume from bigger dimensions to smaller, from bigger height and width to smaller height and width, until it reach the outputs, which can be a logistic outputs, logistic regression outputs, right? To basically to predict whether the fake one is real or not. Okay, so the task of this the discriminator is to predict whether the xi is a real one or faked one. Okay, so but you see there are two components in the case. All these models are learnable parameters. So this one is learnable parameter, and this one is also learnable parameters. These two parts will be learned, will be trained jointly. Okay, so let's look at the example here. For example, the generator and discriminator in this case is to generate fake images from random noise that are similar, that are to compared with the real handwritten digits, right? So the discriminator is a set of convolutional network, and the generator is the opposite deconvolutional network. Okay. All right. So yeah, so the term deconvolution network means that the direction is flipped around. So it's basically the inverse of the original network. Okay. So that's the deconv layer within each layer for this generator model. Okay, and the outcome, the output will be a 64 by 64 by 3, which is a image. Okay, which is a fake image, of course. Okay, so when we train a model, it's actually two parts that we want to train, right? So when we train the generator, we actually sampled data from a random distribution, for example, indicated by this P of Z. This can be a distribution from a random space. And then the generator model can be described by this parameter theta of G, right? And these fake data generated by this generator outputs is basically applies to this distribution, which is we denote it by P of G, okay, which is the distribution of the generated results. Okay, and also we have some real data that is from the distribution of the data, which is P of data. Okay, and the discriminator also have its own parameter, which is theta of D. Okay, so the output of the discriminator basically is about the probability that the inputs is from the real distribution rather than the generated distribution. Okay, and the goal, so here comes how we set up the training loss function or the cost function. So the goal is to train the discriminator so that it can maximize the log outputs of d of x. So basically, we want to train the discriminator to make as good predictions as possible, to be as, it should be able to tell whether it's fake and real as accurate as possible. Okay, and for the generator, the goal is to to cheat. The goal is to trick the discriminator. So we want the generator to minimize this logarithm of 1 minus the d of g. Okay, so we want the generator to generate as real data as possible, to generate fake data that's as real as possible, which makes it difficult for the discriminator to make predictions. Okay, so it's a game of kind of a minimal maxing, min max problem, that we want to the discriminator to perform well, but also we want the generator model to perform well as well. Okay, so it's kind of a cat and mouse game between D and G. We want to train these two parts, interactively. We want the discriminator to be as good, and also the generator to be as smart as possible. Okay, so if we illustrate, so here's the pictures from the original paper, right? So the green line is the distribution of the generated data or the fake data, and the dot line is the real data distribution, while the blue dash line is the outputs from the discriminator. Okay, so at the beginning it looks like this. The green distribution is pretty off from the real distribution. So because there's nothing learned, the generator doesn't know anything about the data, so it will basically generate random noise pictures. But as we train the model, you see, we will first train the discriminator. Okay, so the discriminator at the beginning, oops. So at the beginning, the discriminator is also noisy, right? Because it doesn't know how to discriminate real one from fake ones. So after we train the discriminator first, the distribution will be more smooth, right? Because it knows which one is fake and which one is real very well now. Okay, so the output is very smooth now. And then the next bad step is to train the generator. Okay, by training a generator, we are actually moving this green distribution close to the real distribution, right? Because we want to the goal is to trick the discriminator, and we want to generate as real data as possible. Okay, so at last, until the model converges, ideally we want the fake distribution to be basically identical to the real distribution, and meanwhile the discriminator can do nothing. Basically, this discriminator can only make a half guess, right? It's not differentiate. It's not able to distinguish the real distribution versus the fake distribution at all. So that is the ideal outcome of training a GANs model. But in practice, it's very hard to train to achieve such a goal. Okay, we have to break down the trainings very carefully. So, for example, the step one is to train the discriminator first, right? We want a model to be able to judge. Okay, and then we should generate some fake data using the generator, and train the discriminator on the fake data as well. Okay, and after the first two steps are done, we should train the generator using the predictions of D. And at this time, the discriminator is frozen because we want to train the generator at this step. Okay, so you see these two steps should be basically decoupled. Okay, so we should repeat all the steps until all the fake data seem legit. Seems we basically will need to look at the outputs of the generator by our human eyes. Okay, but this is a very simplistic breakdown of the training steps, and it's 7 years from that first version. So nowadays, all the very realistic, very performance GANs, they require tons of different details to train, to tune the parameters. So there are actually way more details about this particular technique. So that's why we only will have a little peek of the information, peek of the inside of the model. And it's actually tons of details out there to be explored. Okay, so yeah, that's pretty much for the content today. I think we can talk about the midterms, not the midterm, but the final exams on Thursday, on this Thursday. I will open the Zoom room at the same time, and I can also prepare some slides for you to, prepare your review, help your review for the final exams.